Hello and welcome back again to another explanation of how our beautiful world works. So, I don't know why flat earthers are hammering this issue of the moon rotation when they have no explanation for it and it has nothing to do or it cannot be a debunk for the globe. In fact, they tempted me to dig into this issue and make it as globe proof. So what you're seeing here is delirium, and this is not the way I'm going to prove uh, that the moon's rotation belongs to the globe. But just look carefully what's going on. See, the moon is rotating here and there in different direction, and nobody can explain it. But the question is, does it only the moon that rotates? Or is it you, the person with a camera, is rotating in order to capture the moon as it passes almost overhead? And when you spin around yourself 180 degrees or something like that, then the whole sky is turning, not only the moon. So if any one of those smart guys, when they shooting the moon and show its rotation, if he somehow could manipulate the camera to show the stars, he would show that uh, the whole sky is turning as we are about to see right now, sometimes in a rapid rate, as if it's just flipping. All right, so the point is made.
Is there no one else? Is there no one else?
I was on Ron Hagberg channel, his video about the moon rotation, and he has some point of view. He said that everything in the sky moves in cycles. The data comes from years of observations. So this is his explanation of why mooncalc.org, how they make the orientation of the moon phase. The same emotions happened in the past, and they were recorded. The cycle was figured out from that. No, that's wrong. So I made some reply, and the important thing that I need to mention: no need to do more observation to understand our world or some aspect of our world, except to marvel how accurately we know how the world works. I wrote my own program from scratch without studying astronomy or copying NASA, just high school stuff and understanding the heliocentric model. And all these things that I calculated, they come perfectly, exactly as reality. And he said, whatever you say, I don't really care to debate you. Go troll somewhere else. I don't know where is that trolling. I'm just telling him that he's wrong and that the truth is on my side. So obviously he didn't like that and he blocked me. So the moon rotation. Well, first of all, we have to look at this issue. So there's some variables that we need to understand. First of all, this is the moon orientation for three observers. They are watching the moon rise or the moon set. I'm not sure what's this orientation, but the sun is from the right side, and this guy is here above the equator, and this one is below the equator, and this one is way down below the equator. So the first guy, this is what we see, what he sees. He sees that the moon phase is pointing directly downward. And the other guy near the North Pole is watching the moon's pointing down in a certain angle. And the other guy, the third guy, see it in another different angle. So your location on the Earth, your latitude, defines how the moon is going to be oriented for your location on that specific time. So that's the first thing. The second thing is, and let me get back here to this first one. So the variables that defines the moon orientation is your location on Earth, your latitude line, and then the declination angle of the sun, where the sun is, because obviously you can see this is summer. So if it was, let's say, the spring or fall, then you'll need to be on the equator in order to see the moon phase pointing downward. So the your location, your latitude line, the sun declination, and the Earth rotation. All of these three factors control the direction or the movement of uh, the moon phase. So I started to analyze the motion of the moon or stars in the sky, and since it's not the moon that's rotating, it is the whole sky. So I did something here. Let me show you where. Yep, this one. Okay, so the moon and the stars, everything here is spinning according to time or Earth rotation. So let me show you this. If there's two stars behind the moon and we make the moon disappear, those two stars represents the line of the terminator. It doesn't matter if the terminator is curved this way or this way, but the point is this is above the ecliptic and this is below the ecliptic. And in here I'm ignoring the moon inclination angle to the Earth orbit. It is a factor, it sure is a factor, but its effect on the rotation, as far as I can see, is not that much. So, how can we predict the moon rotation or the whole sky rotation? This star has a declination angle higher than this star, and both of them have the same right ascension. Right ascension is the astronomical term for the, let's say, the x-axis of the celestial bodies. So if I'm monitoring the declination angle or the altitude and the azimuth of this star and this star, and I can plot both of them on a chart, then I would be able to see how are they rotating. So that's what I did. My beautiful Excel. So the altitude and azimuth of the low star and the altitude and azimuth of the high star. These are the inputs. I start measuring from the rise of the first star. The highest star represents the top side of the moon, and the lower star represents the lower side of the moon. And then here is, this is the chart here. And this is a chart for the rising and setting of both stars. So let's start working with the inputs. First of all, I have to remove this S because this will give me the rate of the sidereal day. So no, I don't want it to be sidereal. Then I'll put the sun declination, then the declination for the low star and the declination for high star. I just basically I pick the declination angle of the moon and add half a degree and subtract half a degree. Then the time from rising, this is the starting time, and then the latitude of the observer. So let's go and test it. So I'll be using the same observation showed by Ron Hagberg, and it was on the 22nd of September this year, 2019. Okay. All right. So the first thing say that we need to know is the moon declination angle. And to get the moon declination angle, wherever you are on the map, this is your location, and this is the path of the moon during its zenith. So what you need to do is to make this path exactly on top of your location. So that means that the moon is perpendicular to 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 your place, and your location or your that latitude line of yours will be the moon declination angle. As you see, it's getting closer. Okay, there we are. All right, so here, this number, latitude of this location, this is the latitude line, sorry, the declination angle of the moon on that day, 22.2. So I'd say 21.5. The high one will be 22 point, no, say 0.8. And the lower one is 21 0.8. Okay, so that's 1 degree difference. Uh, okay, what else? The sun declination angle. Okay, we go to sun calc and we do the same method as we did with the moon declination, 22nd of September, and we move down, down. All right, so it's almost zero. Oh my God, yeah, 22nd of September. Shit, that's the equinox. So okay, it's minus, let's say minus 0.5. So we go to the Excel sheet and we put minus 0.5. What else? Yeah, the latitude of the observer. So Ron Hagberg observation was near Florida. Okay, here's Florida. All right, so he was questioning why the moon rotates counterclockwise, then halts, then clockwise, then halts, then counterclockwise. Okay, if you notice, the flipping of this motion is when the direction of the moon is along this lines, east or west. But I'm not going to go deep into this. I'll just go to moonrise. Moonrise is it's in the previous day. Damn it! So I gotta go to 21st of September. There is the moonrise here. Okay, now let's see what my spreadsheet says. Oh, what's his location? His latitude was 29.5. Sorry, I forgot to put this. Latitude 29.5. So this is the orientation. There's parallel. Now let's go again to 1 hour after, but let's see the moon set. Sorry, the moonrise is 13 minutes before the new day. So let's go. Oh, sorry. Let's go to the 22nd of September. And 13 and then 47. Yeah. So let's go to 47. That would be 1 hour after the moonrise. Now let's put here 1 hour of rotation from moonrise. 1. Sorry, I think I messed something up. Okay, so let's see. After 2 hours, I rotate to the left, and him after 1 hour, another 2 hours. So yeah, let's say 1:47. It goes to the left. All right, let's add 1 hour. 1 hour here in moon calc. So 2:45 still goes to the left. Let's put that hour here. So 3 counterclockwise. 4 still going counterclockwise. Now let's put that 4th hour here. So it would be 3:47. Okay. Now let's add another hour. Let's be 4:47. Let's add that hour here. 5. Aha, it started to flip to the right side. Now let's say it's 6. Now, and the rate is speeding up. So let's add that hour here. Whoop. Yep, it's turning to the right or clockwise. I think you can see it now. Let's see when it flips. It almost flips at 6:47. Okay, I'm especially interested in 6:47 because that's 1 hour. Let's add 1 hour. Ah, damn. No, add 1 hour, so that would be 7. Okay, another hour. Just flips fast to the other side. So let's add this hour that I made, 7:47. I think you can see it's almost the same angle. I'm not going to overlay it, but you can test that spreadsheet on your own. I'll put a link in the description. So let's see when it goes right again. Well, I have difficulties here with reading the numbers and punching the numbers here, but I think you can understand, or you can see how to use this application. So here we have here the azimuth and the elevation of the moon, or those two stars. So after 9 hours, they continue spin clockwise. 10 hours, 11, 13. Now it started to go counterclockwise again. And let's go back 12. Well, you can see here, this is the azimuth, 280, 281, or the two stars, or the two stars that are above and below the moon. You can play with this number until you see that it's 270, and you'll see that the rotation will change after 270. I'm not exactly sure why, I cannot explain it, but this is the information that I get when I follow the design and the parameters that controls the rotation. So let's see, 14 hours. Yeah, definitely spinning counterclockwise again. 15 hours. Yeah, they continue spinning, but It's now setting, both of them. So that's everything. I protected these cells. So sorry, I protected the whole spreadsheet except for these cells. Um, Here is the sidereal rate and the lunar rate of rotation or spinning. It's not exactly accurate. I just made it roughly. I didn't look for the exact numbers. Not to mention that the moon gets closer and further away from the sun, sorry, from the earth. So this is also a factor that will increase a little bit or decrease. And another factor is the declination angle of the moon does change along the day. So I would recommend that you take the average declination angle, and this average declination angle, uh, my personal opinion about it is during culmination or zenith time. So check the zenith time and find the spot where the moon is the moon path is overhead of your location, and then pick that would be the latitude or the declination angle of the moon. So I think again, it's a globe, and the globe can explain everything with stunning accuracy. Uh, don't look to my humble application here. I just made it in a couple of hours, or just a little bit of time. Uh, my main problem was not the geometry. My problem was dealing with this spreadsheet. As you see, there's a lot of garbage here because I'm not so good at Excel. Well, that's all for this time. And soon I will be making some videos about the Moon Terminator and the Earth Terminator and how can it prove the globe and how can we get some valuable information from it. And as usual, thank you for watching.